Hello and welcome back to Mr. Powers Teaches Algebra. We are still going over rational functions. And last time we talked about the basic of basic rational functions, and that is 1 over x, this guy in blue. It had two asymptotes, one at x equals 0, one at y equals 0. Okay? And we also covered the basic definition of a rational function. It is a ratio of polynomials. Polynomial numerator, polynomial in the denominator. Now, going along with that definition, we also defined a vertical asymptote and a horizontal asymptote, what they are, what the definitions of those guys are. Okay, so now going on with this definition here, if we look at something more complicated, can we tell what these asymptotes will be? Are we good enough at looking at these and saying, okay, I know where this asymptote is, I know where that asymptote is, I know how many asymptotes is going to be? Can we do that? So yes, we can. So here are the rules for doing that. All right. Given a polynomial where the numerator is of degree, I said order in my last video, degree n, and the denominator is of degree m, okay, then the graph will have vertical asymptote at x equals a if the denominator is 0 at x equals a, and the numerator isn't 0 at x equals a. Of course, we don't want 0 over 0. That would not be good. Then we got a tricky thing to deal with if it's 0 over 0. If we have n is less than m, so in other words, if the degree of the numerator is less than the denominator, in other words, the denominator is going to get bigger faster. That's the way you want to think about it. The denominator gets bigger much faster than the numerator. Well, that's easy. That means the x-axis will be a horizontal asymptote. Okay? And that makes sense because at some point the denominator, and we'll look at a couple examples, but at some point the denominator of our polynomial is going to get bigger a lot faster than our numerator. So what does that give you? You get something over a really big number that always approaches 0. Just take a number divided by something really big, you get closer and closer to 0. So that's what happens. If n equals m, in other words, they have the same degree, then then neither one really outdoes the other. Neither one gets a lot bigger faster than the other. The numerator, denominator kind of going at the same pace, you could say, because the rest of the terms don't really matter so much. It's these first terms, ax to the n and bx to the m. They kind of control most of what's going on there. They kind of take over because, again, x to the n is going to get a lot faster than x to the n minus 1. Or you could say x cubed gets bigger way faster than x squared, and so on, right? So what we'll get is a line y equals a over b for our horizontal asymptote. And that makes sense. As values get really, really large for x, these first terms kind of take over, and that a over b is going to be our asymptote. And then we have if n is greater than m, there will be no horizontal asymptote. No horizontal asymptote. So in other words, if n is greater than m. So if n, the power, the degree of the numerator is larger, then this just takes over altogether. And as we plug in larger and larger values, then the whole thing is just going to get bigger and bigger because we're dividing by something smaller than it, and this is getting bigger faster than the denominator. The numerator is getting bigger faster than the denominator. It's just going to blow up. There won't be a horizontal asymptote. So there's your quick talk through about these rules. Quick 5 minutes. I meant to just say, hey, here are the rules. Now let's go look at them. Well, and let's do that. So now let's look at some of these examples and see. Now we're talking about all the horizontal asymptotes here. The first one was the vertical asymptote, and that was the easiest one. And that is really just when is the denominator 0? Because when the denominator is 0, that's when we're getting undefined. And as we get closer to that value that gets us 0 in the denominator, we're getting closer to making the denominator really, really small. So again, the idea is anything divided by a really small number, a number close to 0, blows up, gets huge really fast, but you can never reach that value. So that gives us the vertical asymptote. So let's look at some of those. First one I want to look at is f of x. 4x squared minus 3x plus 2 over 2x squared. So in this case, the power, the degree of the numerator and denominator are the same. They're both x squared. So according to that rule, it's take the leading coefficients of both polynomials. In this case, it would be 4 and 2. The ratio of that will be our horizontal asymptote. And if we do that, 4 over 2, well, that's just 2. Y equals 2. Type that in. And there we go. We can see we get that horizontal asymptote. And we can see if we keep going and going and going and going, it gets closer and closer to that. And we can zoom in here, see that they don't actually touch. The graph never touches that line at y equals 2, but it gets closer and closer and closer. And it makes sense because let's say we want to plug in a value for f of x. Let's say f of 100. Look at that. 1.9851. What about f of 1,000? 1.99. It's getting closer and closer to actually just being equal to 2. 1 over, let's get 10,000. Getting even closer. It's closer and closer and closer. And it makes sense because this minus 3x plus 2, we plug in 1,000. 1,000 squared times 4 is huge compared to minus 3 times 1,000. So that little extra part is not doing a whole lot here when values get really large. And so that's why we're getting 4 over 2. We're approaching that as we get larger and larger values for x. Now, something you'll notice, and this is why I did this example in particular for f, something you'll notice is here we have an intersection point. And that's something a lot of students have a misconception on, a misunderstanding, is they think the graphs can't cross horizontal asymptote. And they can cross it. They can cross it lots of times, not just once. They can go up and down, up and down, up and down, over and over it. In this case, we only got one place where it crosses. So there it is. And so that's just an example of, okay, no, graphs can cross horizontal asymptotes. They can't cross vertical asymptotes. All right? So that's looking at that one. Oh, and then is there a vertical asymptote? Where does the denominator equal 0 at x equals 0? 2 times 0 is 0. And so we do have a horizontal asymptote at x equals 0 right there. You can see that if I zoom out, it does approach that from the left side and the right side, getting closer and closer to that. Okay? Because again, as we get closer to making the denominator 0, it's something, we have some value for the numerator divided by something in the denominator that gives us a very, very big number. Something divided by something very small is huge, right? Something like, it doesn't matter, 8 divided by something really, really small is huge. Okay? All right. Now, we looked at that. What else can we look at? I have more examples. Let's look at g. G of x. Now, this is another example where they both have the same degree. both polynomials in the numerator and denominator, the same degree, so, and same coefficient. So I still got that horizontal asymptote at x equals, or y equals 2. We still got that. Still crosses it even in one spot. But now I got a different horizontal asymptote. In fact, I got two of them. Because 2 times x squared minus 2 is 0 in two places. It's at 1 and negative 1, I think. So we can go x equals 1. We can see there's a vertical asymptote. And x equals negative 1 gives us another one. Another vertical asymptote. So you can see these vertical asymptotes, see the horizontal asymptote. You can kind of see how these rational functions kind of hug the asymptotes. They kind of like to crawl around them. So that's kind of interesting. That's fun to see. Okay, let's see what else we got. In this case, the degree in the numerator is bigger than the denominator. According to our rule, that means we will have no horizontal asymptote. Let's see here. Yeah, definitely no horizontal asymptote. You can see it's kind of weird. We zoom out here. It's like whoop and whoop. There's no horizontal asymptote. There is an oblique asymptote, but I'm not going to go over those right now. But there's no horizontal asymptote. Is there still a vertical one? Yes, there's still a spot where our denominator is 0. If I plug in a 2 here, 6 times 2 is 12 minus 12 is 0. We still have a vertical asymptote at x equals 2. And we can see that right there. So that's very interesting, but no horizontal asymptote. As values get really big in h, they just get bigger and bigger. So h of 50 is 821, or well, anyway. So it's a 34-ish. H of 100, 67. It's just going to get larger and larger. Every time we plug in a bigger number, this gets bigger and bigger and bigger. We get no horizontal asymptote. Because remember, horizontal asymptote is the value we're approaching at large values for our function. So that's not working. All right. Last one I wanted to look at was where the denominator has a higher degree than the numerator. Okay, what's going on there with that guy? So what did it say we were going to do? Oh, yes, it's going to say whenever the degree in the denominator is larger, we always have a horizontal asymptote at y equals 0. That's what it was saying. And again, there it was. We can see it. It happened for sure. It almost touches here, but no, it's not going to touch. Not going to touch. Okay? But anyway, it can touch it. Remember, it's just going to approach it at a very large value. So as we go to the right or the left, it's getting closer and closer to that x-axis in this case, our horizontal asymptote. Now, is there anything else I want to look at here? The denominator is 2x cubed plus 7x minus 23. And when does that equal 0? I put a little thing in here at about 1.75. So if I want to look at a vertical asymptote, where would that be? It should be at about 1.75. Or I could just say L1. Be really lazy. We'll just say 1.75. It's pretty close. So you can see, there it is. That's where it would be. And again, you can kind of see it hugs these asymptotes. Did a weird little loop-de-loop here. But again, these graphs, if we know where our asymptotes are, we kind of know what our graph looks like. We can plot a few points and then have a really good idea of what these look like. Okay? And so that's why I wanted to just show you these today. In the next video, what I will do is show you, we'll do some examples where we try to sketch these out by hand. And so we can see how we can do these by hand. You should have a good idea already just by looking at these examples. Pretty much get those asymptotes, test some points, and go to town. but we'll do some examples together. So until next time, enjoy doing math. Excuse me, enjoy doing math.